So right from our childhood days or even in our studies, we get introduced to certain numbers. So we start with natural numbers, which are obviously involved in basic counting. Then gets added zero. So the number line becomes 0, 1, 2, 3, 4. And we call this as set of whole numbers. So after natural numbers comes the whole numbers. Then there is a notion of direction. So if you are losing something, or if you are supposed to give something to someone, then the negative sign comes into the picture, and so comes the integers. So natural numbers, whole numbers, integers. Next comes breaking up a certain thing into pieces. So you have got half, one fourth, all of these coming into the picture, which are fractions. And you come across fractions at many places in your games as well as around us. In general, the fractions, are called as the generalization of fraction is rational number. So you have P upon Q as a rational numbers, and that's the general definition. And then you have got a lot of rational numbers. After you have learned about, till this part, you can relate to the things, you can see something happening with those numbers. After this comes into picture the numbers like root 2, root 8, pi, and so on and so forth. What are these numbers called? Anybody?
Irrational numbers.
Yes. So then comes these irrational numbers, and then you wonder what these irrational numbers are, and you seem to be very artificial. Although the irrational number comes as simple as you take a 1 by 1 triangle, the hypotenuse is root 2, and that is an irrational number. And by the way, if the number of irrational numbers is more than the number of rational numbers. So you have got this joke which says the rational numbers are outnumbered by the irrational numbers. So this gives another curiosity why there are so many. And first of all, what is the origin of these irrational numbers? And they seem to be not flowing in naturally. So that's let's try to understand if there is some origin associated with, or is there any place where they occur naturally. So we'll go to a slightly offbeat topic now, something called as phyllotaxy. Phyllotaxy is the science for studying the arrangement of leaves on a stem. So typically all of you are aware that the leaves are kind of inserted at different places on the stem, and as the stem grows, you will see leaves growing at different places on the stem. The place at which a leaf originates is called as a node. This is a biological term, and the spacing, the placement, and angle between consecutive nodes or to be leaves is described as the phyllotaxy of a given plant. So the phyllotaxy involves broadly two parts: how many leaves grow up at the same time. So if you would have observed carefully, some plants have only one leaf coming up at a time. Some plants have two leaves coming up at a time. Some plants have three leaves coming at a time. So how many leaves grow up at a point, and how are the consecutive leaves separated? So how do two consecutive leaves or pair of leaves separate themselves? So you tell me, what is the key objective of leaves? So what is the function that a leaf plays in the plant? Anybody?
Photosynthesis.
Yes.
Making
And what
food.
does that? Yes. So
Making food.
photosynthesis results in making of food, and that is what is the key function of the leaves. And for photosynthesis, what is important?
Carbon dioxide.
Okay. And
Light,
Sunlight.
very good. So for photosynthesis, carbon dioxide and sunlight are important. Carbon dioxide is abundantly available. That's not a challenge. So the real challenge is
Get sunlight.
sunlight. So the key function of leaves is preparation of the food. And what is important is all the leaves should get fairly equal exposure to the sunlight. So unless there is sunlight reaching every leaf, the function of that leaf cannot take place properly. And then the other function that leaves also have is channeling the rainwater towards the span of the roots. So you might not have observed, but typically the leaves also play a role of channeling all the water, rainwater that falls down onto the roots. Okay. So this picture broadly gives you an idea of what is node. So the point at which a leaf is growing is called as node, and the separation or the region between the two nodes called as a internode. Now, the way plant grows, somebody has unmuted and there's a background noise. Can that be checked? Okay, so let's understand how the plant and the leaf growth can be picturized. So there is a leaf at the top of the, or what is called as apex. A leaf comes up. Then what happens is that the stem turns by some angle and it rises up. So while growing, the stem grows up. So it not only grows up, it kind of takes a twist, and after that twist and a slightly height rise, a new leaf comes up. So this is what would have been the first leaf. Then there's a increase in height, and then the stem slightly turns, and then the new leaf comes up, and this cycle continues. So everybody is with me so far. First leaf, there's a slight increase in height, then the stem turns a little bit and new leaf comes up. That's how the growth happens, and this cycle continues. Now let's see some examples. So let us look at some of the very simplest growth patterns. The simplest one is the stem turns up by 180 degree and a new leaf comes up. Okay, so for example, here you have got the first leaf. The stem has turned by 180 degrees, slightly grown up, and you have got another leaf. Then after this, the stem has turned by 180 degrees, new leaf comes up. So you can imagine this cycle going on. Agree? Okay. So now, if you look at from the top, section, this is how it would appear. You would have first leaf, 180 degree, second leaf, 180 degree, turn, third leaf, 180 degree, so on and so forth. So this is the topmost part. So this is how the growth will happen. Now let us look at some plants which show this kind of a pattern. Can all of you observe this leaf? Okay, so this leaf, then 180 degree, half a degree turn, this new leaf, half turn, new leaf, half turn, new leaf, so on and so forth. All of you can observe this very clearly. Okay, now let's look at another example. First leaf, half turn, second leaf, half turn, third leaf, half turn, so on and so forth. All of you can clearly see this. Can anybody identify which plant is this?
Karipatta.
No, this is Harbara. Okay, so this is early Harbara. Then you would see a lot of bush kind of a thing happening. But this is Harbara. Okay, so what is happening here is the growth pattern is that it is turning by, it is taking a turn of half. Okay, now let us look at some more example. Okay, leaf, half turn, another leaf, half turn, third leaf, half turn, fourth leaf, so on and so forth. This is Sontakka. Many of you would have seen this or know this, right?
Yes.
Now this is Avla, the big Avla that we get again here. leaf coming up, half a turn, leaf, new leaf, half turn, so on and so forth. It is kind of alternate. Did anybody want to ask any question? I heard some noise. Okay. This is another example, Sitafal. Okay. All of you can clearly see the stem is turning by half, new leaf coming up. Turning by half, new leaf coming up. Right? Find this pattern easy to remember. You can see kind of alternate leaves.
Yes, sir.
Okay. Okay. Now let's move further. Let's add more leaves. So what do you see here? This is typically the what we call as ova plant, and this is used for making bhajis. So as you can see here, this is the first pair of leaves. Now what is happening? Instead of a single leaf, a pair of leaf is coming up, and then the stem has taken a half turn. You can see them perpendicular to each other. Next pair of leaves taking half a turn. Here you can see it, right? This is another one, which is mint or pudina. Again, two pairs of leaves taking a turn, another set of leaves appears. This is golden duranta. Again, you can see typically along the compounds and so on and so forth. But again, two pairs of leaves coming it and it taking a turn. More examples. This is Ananta tree. This is cactus. So you can see it many places around. Okay, let's add further more. Now, can somebody explain what is happening here?
3 leaves are coming up.
3 leaves.
Very good.
And then taking half a turn and another side, but alternately they are growing in the gap.
So will this be half a turn? You look at the relative placement of those triplets.
120 degrees.
So it is a 1/3 turn.
Okay.
Okay. You can beautifully see it, right? It is taking a 1/3 turn, and then new are coming up, and that's how they are one day next to the other. Okay. And if you see it from the top, you will observe them like this, and that is where, as you mentioned, it is 120-degree turn, right? Okay. So this is how the growth will happen. Now let's look at some more examples. This is another creeper.
Plant. So this was the plant.
Sorry?
It was this plant.
Unfortunately, I don't have the names of each and every one. Okay. So these
it's
are
okay. It's okay.
these are the,
that's fine.
yeah, these are the snaps I have taken.
Okay.
That I found. It. Okay.
Yeah, thank you, sir.
Okay. So here you are taking a 1/3 turn, right? Okay. Now, what did we start with? Okay. When the prime objective of leaves is to cook food, and to cook food, everyone should get fairly equal exposure to sunlight. Now, if you are turning by half, the first and the second leaf is fine, right? What about the third leaf? The third leaf has no choice but to directly come over the first leaf. All of you agree? Right? And that's where every alternate leaf is on top of the other leaf. Right? Now let us go to this turn by 1/3. So what do you observe here? The first, second, and the third leaves will be okay, but the fourth leaf will has to get over the first leaf. All of you agree?
Yes.
Right? So every fourth pair of leaf will be coming on top of each other. Right? So that means, so I'm giving these examples. So here you can see Tulsi. Okay. So you can see a turn by 180 degrees or half a turn. So these two leaves are directly on top of the earlier leaves that have come up. these two leaves are directly on top of this. So as far as the leaf is small, that is, it is in the infant stage, the others will get enough sunlight, but as soon as this grows, it is going to cover up the other leaf, right? This is Kaner. Now you have got three leaves coming up at a time, and obviously you can see this layer is covering this layer is covering this layer. So here every fourth layer is on top of the first layer, right? Same is the case with Pudina. Okay, so every alternate layer is on top of each other, right? Now let us try to find out what is the best possible arrangement to avoid an overlap. So if you turn by half, every third, after two leaves are okay, third leaf comes on top of first. If you turn by one third, you will have something coming up. Dot dot dot. If you take a turn by 1 by n, what will happen? The first, second, third, nth leaves will be fine. But what will happen to the n plus 1th leaf? The n plus 1th leaf will again get over the first leaf. If you agree this?
Yes.
Okay. Now what if I turn by m by n? Okay, 2 by 3, 5 by 7. Okay, let us take this example 2 by 3. So this is the first leaf. Now it takes a turn by 2 by 3. You will have the second leaf. Again, it will take a turn. You will have the third leaf. Now it takes another turn and you have the fourth leaf. So what do you observe now? The fourth leaf has come on the second leaf because it is 2 by 3. The fourth leaf has come on top of the second leaf, right? So in general, if you turn by P upon Q, what will happen? Anybody? So first, how many leaves will be okay? What will happen to a particular leaf?
Two peaks.
Yeah, explain it fully.
Few leaves are fine. First few leaves will be fine.
Very good. And what will happen to the Q plus 1 leaf?
It will get over the first pth.
So it might get over the first or the pth. So now that is something that you may have to try and just do it and let me know. Okay. But moral of the story, if you turn by P upon Q, the Q plus 1th leaf again will come over some previous leaf. All of you agree to this conclusion?
Yes.
Yes.
Okay. So if you don't want to have a complete overlap on the previously grown leaf, so what that turn has to be? That turn cannot be a P upon Q. So the turn has to be an irrational number. So it cannot be P upon Q. It cannot have a simple decimal. So it has to be a non-recurring, non-terminating decimal. And that is where irrational numbers arise very naturally and nature has created them. So is first of all everybody convinced that P upon Q, if you take a turn by P upon Q, the Q plus 1 is going to overlap. And you have to have some number that doesn't have the form P upon Q. And that number is the irrational number. All of you agree to this?
Yes.
Yes,
That's
sir.
beautiful.
Okay. Now let us see. Thank you. Now let us see if do we really see or have such arrangements. Okay. Now I have taken some snaps. So here you can see these leaves are not going on top of each other, but there's a slight angle. And when I take a top view, you can see that there is no particular leaf which are directly on top of each other. Yes, there will be some overlap, but they are not directly on top of each other. Okay, this is a Tamalpatra plant. The very simple plant of Terda. I don't know how many of you have seen the Terda flower.
Yes,
But
sir.
okay, again these leaves are turning, the stem is turning, leaves are coming up. If you take a top view, what do you observe? No two leaves are directly on top of each other, right?
Yeah.
Okay. Bougainville, all of you know Bougainville. So try to look at it from a top view. Again, even if you look at in the side view, you will observe that they are turning in such a way that you get this spiral arrangement. Sunflower. Okay, you take a top view, and then you can clearly see that none of them are on top of each other. This is another plant I found, but I don't know the name of it. But it is growing so beautifully. You can actually see how it is growing like a
Insulin plant, sir. Insulin plant.
What is the name?
Insulin plant.
Oh, insulin. Wow. Great. I wasn't aware of this. But you can see how beautifully it is encircling. And then you can clearly see that there's a very nice pattern here. Okay. So indeed, our hypothesis that is there such a growth possible? Yes, it is possible, and it is actually happening. Okay. Some other examples. This is again a show plant, but you can see the way the whirl is happening, or the way the spiral is going around. They are not going to overlap on each other. This is simple sadafuli. Even in cactus, you would see this arrangement. You would have noticed this cactus plant already. This is known as cycas. So CYCAS. Again, I couldn't go on top and take a top view, but it is clearly spiraling in such a way that all leaves are going to get equal ones. So even if you look at palm tree or coconut tree, you would see that kind of a nice spiraling and twisting pattern. So essentially, as you can see, the leaves are spiraling as they grow along, and the angle between them, or the turn between them, is maintained in such a way that there will not be a complete overlap. So these are some animations which we have tried to do, and then you can see none of them are directly coming on top of each other. Apart from leaves of a plant, just what are the other places that you can see? So this is the flower which is going to show these arrangements. Now again, this is a beautiful show flower which you would have seen at many places, and you would clearly see that kind of
Hexera plant, sir. Hexera plant, red one.
right. This is rose. You can see the petals arranged in such a way that no two are completely on top of each other. Pineapple. The arrangement of scales as well as the leaves. Again, the turning and twisting happens in such a way that the arrangement is beautiful. So petals, seeds, flower placement, all of these growth patterns also show similar arrangement. So this is again beautiful sunflower. The simplest flower of Tantani, I don't know what in English it is called, but this is the most roadside plant and most ignored plant. But that shows this beautiful arrangement. This is mohacha jhad. Again, you can see that beautiful arrangement happening. Okay, so we have seen what is the drawback of a P upon Q kind of a number, and if you don't want to have that drawback, you have no choice but to use some irrational number, and the nature does bring up that irrational number. So what is this particular irrational number used by the nature? So that would be the next interesting question. The answer turns out to be this irrational number is what is called as the golden ratio, or phi, and its value is 1.61803398887, etc. Let's see how does this come into definition. How is it defined? So by definition, if you have got a line segment which gets divided at this point in such a way that the ratio of whole line to the major part is equal to the ratio of major part to the small part. Let me repeat. Divide the line segment in such a way that the ratio of the whole segment to the major part is same as ratio of major part to the small part. And that is the definition of the number 5. And that's how phi, I mean, if you convert this into an equation, it leads to the quadratic equation x square minus x minus 1 equal to 0. So this is the defining equation of phi, and obviously the root of this equation is 1 plus root phi by 2, which is 1.680339 dot 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 dot. So this is the origin of this number phi, and the beauty is 1 plus phi is phi square, or phi square is equal to phi plus 1, and that's where the equation that you have to keep in mind is x square is equal to x plus 1. So that is the origin of phi. And now let us see where else do you see phi. Okay, so if you take 3 equal lines, okay, this is the first line, second line, third line, place the first line or stick the first line at the middle of the, stick the second line at the middle of the first line and stick the third line at the middle of the second line, and then the ratio that you get is again phi. Now if you have a circle and if you insert an equilateral triangle in the circle, so this is another good problem. What is the equilateral triangle possible inside a circle? But we will not go to that. But if you insert an equilateral triangle and then take its midpoint and extend that, then this AB and BG is again giving you phi. Another example is circle on the diameter. Again, AB and BG are going to lead you to phi. Insert a pentagon inside a circle and then join these two. Again, this ratio will be phi. Okay, let me take a pause here. If you have got any observations, any comments. Okay, if not, let's proceed. Now, let us look at some algebraic expressions. While we have seen some cases, let us look at some very odd, peculiar looking algebraic expressions. So what is this expressions? Root 1 plus another root inside 1 plus root inside, and so on and so forth. So this rooting goes on and on and on. So this is something called as nesting. Okay. So now let us find this number. So if you want to find this number, let us call it x. Now how do you go further? If you want to find this number x, you have to do something with it. What is the next thing that you will do? What are you seeing on the right hand side? The right hand side, you are seeing square root sign. So what is the first thing that comes to your mind when you say yes?
Square both the sides.
So
Squaring both the sides.
let us square both the sides. So what will be x square? It will be the first root will go, okay, and then it will be plus root of 1 plus root of 1 plus root of 1 plus root of 1, so on and so forth. All of you agree? Yes. Only the first square root has gone, everything else is as it is, right?
Yeah. So 1 plus x.
Now what is this expression again?
X again.
It is the same expression that we started with, because it is infinitely flowing. So this is simply 1 plus x. So what do you get? You get the expression x square equal to 1 plus x. And that is again a defining expression for
phi.
So this expression, this particular peculiar expression is another representation of phi.
Fine.
Okay, such expressions are called as continued roots or nested radicals. Just as an interesting point here, Ramanujan had posed this problem in the Journal of Indian Mathematical Society. What is root 1 plus 2 root 1 plus 3 root 1 plus 4 root 1 plus dot 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 dot. Any guesses whether this will be a finite number, this will be a rational number, irrational number? Any guesses? Do you think this will be rational or irrational?
Irrational.
Okay. Incidentally, the answer turns out to be 3. So
Oh.
even if you see very odd looking expressions, sometimes they end up being very nice numbers. Okay. So this is one algebraic expressions. Now let us look at another algebraic expression. Okay. Let us look at this expression: 1 plus 1 upon 1 plus 1 upon 1 plus 1 upon 1 plus 1 upon 1, so on and so forth. Okay. Again, this ladder goes on and on. So we want to find this, what this is. So let us call this x again. Now I'm going to do some trick. Okay, I'm going to cover this part and cover this part. What remains?
X.
Again, it is the same flowing, right?
Yes. Is X again.
So this is x again. So how will you want to express this? So this x 1 plus 1 upon x is again equal to x. 1 plus 1 upon all of this is again x. So 1 plus 1 upon x is x. So you simplify this. Simply cross multiply. You will again get the, yes, you will again get the equation x square equal to 1 plus x. So this is again the defining equation for phi. So again this funny looking expression gives you phi. Okay. Now such expressions are called as continued fractions. Okay. Now that we are looking at these odd and funny expressions, let us learn a little more about them. So in general, if you have this particular expression, it is called as a continued fraction: a naught plus b naught upon a1 plus b1 upon dot 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 dot. Okay, and if all of these b naught, b1, b2, b3, all of them are 1, then it is called as a simple continued fraction. So how will a simple continued fraction look like? It will be a1 plus 1 upon a2 plus 1 upon a3 plus 1 upon and so on and so forth. And in a simplest form, it is represented as a1 comma a2 comma a3 comma dot 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 ak. Okay, so an example is 1 plus 1 upon 2 plus 1 upon 3. So you can continue dot dot dot, or you can end it at some point of time. So when you end it at some particular point, it is called as a finite continued fraction. If you continue, then it is an infinite continued fraction. Okay, now again, are these continued fractions something artificial? I mean, they look artificial, right? But we have seen that one of them results in this phi. So let us try to see some examples. So can you have a normal fraction expressed as a continued fraction? Okay, let us try the fraction 40 upon 13. I'm just taking some two numbers. I'm sorry, it is 50. So I wrote 40 there. So there is something called as squaring the rectangle. So let us look at a rectangle which has got sides of 50 and 30. What you have to do is you have to go on fitting squares inside this. So what will be the first square that you can think of that will fit inside this? A square shape. What will be the dimension of that?
13 by 13.
Very good, 13 by 13. Okay, so you can fit the square of 13 by 13. How many such squares will fit here?
3.
Very good. Okay. 13 threes are, and then what will remain? You will be left with 11.
Rectangle.
11.
Yes.
Correct?
11.
So you will be left by 11, and then you will have another rectangle which remains 11 by 13.
31.
Okay.
Correct.
Now let us try to do some algebraic expression over this. Okay. 50 upon 13 is equal to this 13, 13, 13 3 times plus 11 upon 13. That is, now you can simplify this. 3 plus 11 by 13. All of you agree?
Yes, sir.
Okay. Now I'm going to do a little trick. This 11 by 13, I'm going to write as 1 upon 13 by 11. Everyone with me so far?
Yes.
I'm just doing a reciprocal. Now, what is it that we are doing? We are trying to go on fitting squares here. So now this is 11 by 13 remaining portion. So what square will fit in here?
11 by 11.
Very good. So let us put that 11 by 11 square. What will remain?
2 by 11.
2 will remain. Okay. Now let us do some work here. So 13 by 11 is 11 plus 2 upon 11. Okay. That is 1 plus 2 by 11. Everyone with me?
Yes, sir.
Now what is the next thing that I am going to do? What is the next trick that I will do now?
2 by 11, write it as 1 upon 2, 11 by 2.
Very good. I am going to write this 2 by 11 as 1 upon 11 by 2. Everyone with me so far?
Yes,
What is
sir.
the next thing that I will do now? I have this remaining
Yeah.
area to fill. What will go in there?
5
2 by
square.
2. 2 by
2
2.
by 2 square. Okay. So how many 2 by 2 square will go in there?
5.
Very good. 1, 2, 3, 4, 5. And what will be the remaining space? 1 by 2, right? This remaining
Yes.
part will be 2 5s are 10, and this remaining part is 1, and you have got still 1 by 2. Now let us go to the algebraic expression. So this 1 upon 11 by 2. So this 11 I am going to split as 2 plus 2 plus 2 plus 2 5 times. So this is 5 plus 1 by 2. Okay. So 50 by 13 we have expressed it as 3 plus 1 by 1 plus 1 by 5 plus 1 by 2. So does this look like a continued fraction?
Yes.
Yes.
Okay. Now we are left with this fellow. So what trick I will do here again? This 2.
2 by 1.
I can write 2 by 1, but again 2 by 1 is, it is again 2. Okay. So you don't need to break it up further. But what we will do is, this becomes the continued fraction form. So it is 3, 1, 5, 2. All of you agree? This is
Yes,
the
sir.
continued fraction. Okay. And then we will fill these remaining with square of 1 by 1. All of you agree?
Yes, yes.
So now have we completed squaring the rectangle?
Yes.
And in that process, we have got a continued fraction
Continuous
representation of
fraction.
this particular rational number or this particular fraction. Now let us note some observations. Okay. So with this continued fraction, we got as 3152, and we filled all of this. So we have got 3 yellow squares of 13 by 13, 1 green square 11 by 11. Next, can someone tell me?
Orange.
4 orange
How
squares.
many?
4 orange
Okay.
squares.
5. 5.
Yes.
5
5
orange
round
squares and 2
2 by
yellow.
2.
2 yellow.
Right? Okay. Everyone with me so far? Now let us try to do something again which is totally different. So let us try to find the GCD of 50 and 13 using Euclid's algorithm. Do you remember how do you find GCDs? I hope it is very simple. So what is the first step you take? You divide 50 by 13, right?
Yes.
Then 50 is equal to 3 into 30 plus 11. Okay. What is the next step you do? Can anybody remember and tell me?
The divisor becomes dividend like that.
So this
11.
11 is equal to
and you will divide it by 11, correct?
13 is equal to 1 into 11.
1 into 11 plus 2. And then 11
divided by 2.
divided by 2. 5 into 2 plus 1. Okay. And then 2, 1 into 2 plus 0. Okay. And then this is the way you find the GCD. And each of these steps corresponds to fitting that square inside that rectangle. Do you realize this? Okay. So this is the beauty. And then what you call GCD of these two numbers? It is the second last number, right, in this flow. So the GCD of these two numbers is 1. And what is that 1? It is these last squares that we actually fill in there. Okay, do you find this interesting, beautiful, exciting?
Very, very, very much interesting. And the first time I'm learning this. Very happy. Just never noticed this kind of thing.
Right, right. You will have all of them separately put up, but you wouldn't find them put in this all of this together. So 3 things. Any fraction, we are expressing it in a continued fraction way. That is reflecting in squaring the rectangle, and that also relates to the GCD. So do you want to do one more example?
Yes, sir.
Okay, let's do 88 and 36. So what will be the first square that will go in?
2 squares will get 36
Okay.
to the 72.
Correct. 36, 36, 2 squares. And at the same time, we have to find the continued fraction. So you will be remaining will be 16 and 36.
Okay. Yeah.
So 88 by 36 is 36 plus 36 plus 16 upon 36, which is 2 plus 16 by 36. What is the next thing that I am going to do for this algebraic expression?
2 squares of 16.
2 plus 1 upon.
Yes, I am going to do reciprocal.
Okay.
And then what will I do? I will have to fill this square, fill this rectangle. So you will have
2 squares.
16 by 16. Very good. 2 squares of 16 by 16. And remaining will be 16 to the 32, 4. Now let us come back to the algebraic expression here. It is 1 upon 16 plus 4 upon 16, which is
2 plus 4 by 16.
2 plus 4 by 16. Okay. Now what remains? This space.
It will be
What trick I am
4
going
by
to-
4.
completed.
4 by 16 I am going to write as 1 upon 16 by 4. And then I have to fill this square now, this space now. What will go in here?
4 plus 4 का 4
4.
square.
4
4.
squares.
4 by 4.
4 squares.
Yes. Is this completely filled?
Yes, yes.
Yes.
Do you need to go any more further?
No.
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 No. So you have got this expression 88 by 36 is 2 plus 2 plus, I'm correct, 2 comma 2 comma 2, 2 comma 2 comma 4. The square is completely filled. You got the continued fraction. Now what is the next fun that we want to do?
You
Sir,
cleared
one
it.
doubt is there. Sir, one
It is-
doubt is there.
Huh.
Doubt in the sense, sir, will we get all these videos at the end of learning process? Because we are not able to note down very far. It is we are in time right now.
Yeah, I can go slow, but I think you will get these videos. Gitanjali and Mandar, they will
Okay,
let you
sir,
know,
thank
right?
sir.
Okay, so the next thing I want to do is GCD. So let's do the GCD. So 88 is equal to 2 into 36 plus 16. Now you take 36 here, divided by 16. Right? 36 is equal to 2 into 16 plus 4. What is the next thing that you will do now?
16 divided by 4. Yeah.
16 and 4.
divided by 4. 4 plus 4. 4 into 4.
Okay, these correspond to these 2 yellow squares, 2 green squares, and 4 brown squares. Now, if you recall again by your GCD step, second last remainder is the GCD, and that corresponds to the last squares that were put in. Right? Enjoying this?
Yes, sir.
Yes.
Yes.
This division algorithm also side by side we are learning along with squaring the rectangle.
Right. So all of these you have learned in the school. It is just I'm giving a different representation of that. Okay. So these continued fractions that we saw, we initially felt them they are very artificial and odd, but as you can see, they are also very natural and interesting, and we can express every fraction as a continued fraction. Every rational number you can definitely express. These come up naturally in squaring the rectangle. They also relate to GCD or HCF. And again, going back to where we started with, we've started with the need to have irrational numbers, and then we saw some continued fractions. And then you have got a theorem which says that a number is rational if and only it can be expressed as a simple finite continued fraction. So all the fractions that we saw were finite, because rectangle will definitely get filled up with squares, and the worst case will be a 1 by 1 square, right? So every finite number, every rational number P upon Q can be expressed as a simple finite continued fraction. This also means that if you have got an infinite continued fraction, then that number has to be irrational number. Okay.
Sir, one thing is, if instead of rectangle we try to fill a triangle with squares, then what will happen?
Triangle cannot be completely filled with squares. Na? You will have corners.
No, will it be irrational?
No, but you cannot fill the triangle completely with the squares. Na?
Oh, yeah, that is true. But then will it represent an irrational thing or no?
No. So essentially that particular methodology will not work is what I am trying to tell you.
Okay, sir.
Okay.
It can never be equal, so you cannot equal.
Yeah, it won't be equal. Okay. So now every irrational number irrational numbers always have an infinite continued fraction representation. Okay. And where did we start with? We started with this continued fraction 1 plus 1 by 1 plus 1 by 1 plus 1 by 1, which is the most basic and the simplest continued fraction you can have. And that is our number phi. Where did this phi number come from? It came from the leaves or the arrangement of leaves or arrangement of petals, and then from the growth of plants that we see on the leaves. Okay. Now, depending on how the twist and new leaf comes up, you would see anyway the plant has to grow. So you would see different growth patterns of the plants. Okay. So if you have got this Sontaka plant, you know that it is having the second leaf, alternate leaves on top of each other. So you would never see a branching of Sontaka, and you will see always a new Sontaka branch coming from the ground. Right? I mean, those of you who have seen, or otherwise this photo brings that up.
Yes,
okay.
sir.
Next is this Aula. Okay, you have got this alternate, and then if you look at the whole Aula tree, everyone has to get light. So all of them will just spread here and there, and you would never have a nice arrangement, right? Because everyone will fight, and then new branches will come up to get more sunlight. So this is the pattern that is shown. Now, Pudina, again, after 4 or 5 layers of leaves, they are going to come on top of each other. So it is try spreading in all direction, or you'll have new shoots coming up at different places. Okay, Tulsi. So you would see it growing all haphazardly, because just to avoid overlap, a new stem will come here, new stem will come here, and so on and so forth. Only small packets will remain in that pattern. The rest will be what is called as a profuse growth. So this is canary. And then you will see, funnily, when it branches out, it also gives 3 branches at a time. So you will see all circular growth, or not circular, but you will see very crowded growth to get sunlight. Okay, so we almost come to end of the hour. So what is it that you will do next? My expectation is that you would have developed interest in looking at the trees again, but from a different perspective. Try to find out the phyllotaxy, learn a little bit more about phyllotaxy, and then looking at the phyllotaxy, try to estimate what will be the growth pattern. For example, Zai, Zui, all of these creepers, if you observe them carefully, all of them turn by half a degree for a new leaf. And to be able to sustain sunlight, they are going to creep all over. So it is, I mean, the growing pattern is very much linked to the phyllotaxy and the arrangement of leaves. So try to find out such patterns, and then you can share those photos with me. As I said, you will yourself start realizing and looking at trees differently now. Now, so far, you are looking at irrational numbers as something very odd or something very unnatural. You will start now loving them possibly. Then you can also play around with continued fractions, do some squaring of rectangles, GCD with kids around, and share your experience. Thanks a lot.